All right, welcome to this exponential growth functions review. What we're seeing here is the graph of an exponential function. You can see that it models things that grow rather quickly. As it moves further down the x-axis, the y-axis goes up very quickly. Now previously we dealt with functions such as f of x equals x squared, where the variable x was the base and the number 2 was the exponent. Now, in exponential equations, we're dealing with where the variable is the exponent rather than the base. So the variable is what is changing in the graph. So the exponential function has a base, or in this case b, a product a, what's being multiplied to b, and an exponent x, which is in green there. B is going to be the base, which is the fixed number, and the exponent is what's changing and is what we call the variable. Now, this is a helpful tool to help us remember that an exponential growth function happens when the base is greater than 1. When the number 1 is raised to any exponent, it always equals 1. Our example is 1 raised to the 13th power. It's still going to equal 1, no matter how big the exponent is. But any number that's larger than 1, in our case 1.01 raised to the 13th power, is growing. It's growing slowly, but it's still an exponential growth function. In this case, 1.01 raised to the 13th power equals 1.138. Here is just a regular exponential function. We have y equals 3 raised to the x. Since x is the variable and it's the exponent, you can see our table of values here for x. At minus 2, y is just a fraction. When we move all the way up to 3, it's going to already equal 27. And as you can imagine, 4 is going to be larger still. It's going to actually be 81, and it continues to get large very quickly. Now we have a problem here that we worked on in class. This is the case where we're seeing population growth. So the example is, in 1992, there were 1,219 monk parakeets in the United States. What you have to do is plug it into the equation, and in the next 11 years, with about a 12% growth rate, how many parakeets are there going to be in the year 2003? Well, if you just use the equation y equals ab raised to the x, you're probably going to get the wrong answer because you have to add that percentage to 100. So if you use 1.12 as your base for b, you'll get the correct answer when you raise that to the 11 as the exponent. This exponential function has a base, a product, and an exponent, just like our previous one. But in this case here, we can see that we still have the product being the initial amount or the starting amount. Now our exponent has changed to t, which represents the time. In this case, it's going to be in years. And r is going to be the percent increase, or how much has been increased in the monk parakeet population. So 1 plus r is going to be our base, and that's what we call the growth factor in a time exponential function. So the setup of the monk parakeet problem looks like this. We have y equals 1219, our product, times 1 plus 0.12 or 12% growth for our base, and 11 for the amount of years that we're raising it to the exponent. We're going to get 4,240.35 birds. Now, of course, we don't get 0.35 birds, but then again, for our exponent, we're using years and not a more exact or continuously compounding exponential function. That brings us to translations. Now we've dealt with translations in the conics section of our unit. Now we're dealing with translations of exponential functions. So a translation is when a graph is shifted up or down or to the left or right. Y equals a, the product, times b, the base, raised to the x, the variable, exponent. That's going to be our parent function in this case. In a translation of that function, our parent function, the equation looks like this. Y equals ab, that's the same. And then the exponent is going to become x minus h, and then we have plus k, or the constant. In this case, h in the exponent is going to be the number of units translated either to the right when it's positive or to the left when it's negative. K is going to be the number of units translated up when it's positive or down when it's negative. In this case, to avoid some confusion, when h is a positive number, it's going to be x minus that positive number for h. So that will go to the right. If h is a negative number, it's actually going to look like x plus h. In that case, it will go to the left. An example is when you graph y equals 4 times 2 raised to the x minus 1, and then all of that minus 3, as well as graphing its parent function, which is y equals 4 times 2 raised to the x power. You'll see that the first graph will be translated 1 to the right and 3 down from the parent graph of 4 times 2 raised to the x. And anytime that you graph a function and then its parent function, you can see what it's going to be translated by what's in the exponent, in this case the 1, and what's the constant, in this case minus 3.